Welcome to another GCBASIC demonstration for the PIC18FxxQ24. This is part 14. I've called this pulse width modulation many ways. Let's get into it. So first things first, please. First things first? Yep, this is what we're doing. First things first, I need you to like and subscribe to the channel. Like the video, let the video run all the way through. Those metrics are extremely important. Okay, so what we're looking at is, as in bold, that's like the sixth bullet down, pulse width modulation, PWM. There are many ways of doing that, not only within the capabilities of the chip itself, the Q24, which is a high performance PIC18, but there are other ways within the language of GCBASIC that supports generating signals that look like a pulse width module. Oh, why did I say that? Pulse width modulation. Now, so PWM is what I'm going to use now, and we're going to look at it in many different ways, including the ones within the microcontroller itself. That's CCP, PWM, and 16-bit PWM. We'll look at both of those as well, but there's many different ways. So we're looking at it in 6 ways to dim some LEDs. And we'll look at my desk, the setup on the desk, slightly different, but I'm assuming that you've installed all the software. There is no hardware, just the LEDs on this one. We're going to put everything out to the LEDs. So I assumed you've got your software installed. You can program it. You've got a Q24. You've got 4 LEDs that are operating. Best go back to one of the early demonstrations before you start this, and you have a pop because we're going to use that. This one, we're not going to use the switch, but we are going to use the USB serial TTL connection. So, a couple of things we need to talk about. Are we using the power domain today? No, we are not. However, if you chose to change the program and you were going to output something let me turn the pen on, in this green, if you were going to connect up to these green ports here, or pins some may call them, you must apply voltage to the VDDIO2. It is a power domain that is separate from the orange one that you normally put 5 volts on. So if you wanted to run this at 3 volts and the main one at 5, you can do that, but I am not using VDDIO2 today. However, you'll see the connection is still there. So what am I focusing on? I've got 4 LEDs on port B, 0, 1, 2, and 3 respectively, and I've still got the transmit for the serial line on port C.6 and the VDDIO2 connected to this pin here that used to be called C7. VDDIO2. Critical if you're using that green zone. Great. So what is a PWM signal? This is exactly what we're going to see. We're going to see an LED get brighter and darker depending upon the duty cycle. Now, I will explain this in some detail shortly, but all we're going to do is vary the pulse and vary the duty cycle to change the LED, and it's great for controlling other things, but it's essentially what we're going to be doing. And it really is, PWM is really a succession of pulses, and it's reducing the average power delivered by an electrical signal. It just chops it up into discrete parts. And we're going to see that we can do that so many different ways, but it's extremely useful for controlling motors, LEDs, and other control signals. So it's the average that the LED will be actually consuming in terms of the power to actually make it brighter or darker. And it really is this turning it on and off, on at one rate and fast off. So it's on and off, and it gives you that average rate. And we can see that quite quickly. And we're going to look at generating different ways. I mean, so many different ways you can do this, okay? There is a legacy method, which is still extremely useful just for sending out signals, a set number of signals, fixed frequencies, 16-bit signals. This is just a terrific area to look into. So we're going to sort of skim across the top of it. So what have I got today? I've got an oscilloscope hooked up. This is not the signal you'll be seeing, but it's an oscilloscope hooked up into one of the LEDs. Let's look at desk cam, and that will sort of lay it out. Here is my oscilloscope. It's actually from Gabtronics. I've had it for many years, and it's extremely useful because it enables me to show you what's actually on the screen, which is fantastic. So if I pop back to my main screen here, that's the actual signal coming off the LEDs at the moment. And if I change the potentiometer, well, I haven't got that actually programmed yet, but we'll look at that shortly. What else have we got in here? I've got a bigger oscilloscope attached to the same LED. And here is the LED that's actually on at the moment. This one here. You can see there's one LED, but there's actually 4 LEDs that are there. And I've gone back to the board I was using previously. Q24 programming cable here, which is a PIC18FxxQ24. What else? Here's my VDIO signal, VDIO2 signal, and here's my potentiometer that we'll be using shortly. So what we're going to do is make these LEDs change, and we can see all that happen through things like this oscilloscope terminal. It's a terminal into it, or we might look at the Rigol, just depending how I feel at the moment. But they're all generating the same. They're all measuring the same signal. The Gabtronics is a lot easier to use in terms of the interface, but its frequency is limited. Okay, as you can see, there is a very different signal being generated in the oscilloscopes. So that's my setup. But what we're going to do is look at many different ways. Okay, so one is the simplest way. We're just going to turn the LED on and off, and that will generate a signal, and you can do that on any port that's an output. You can use PulseOut. PulseOut is a GCBASIC internal command, and it will pulse the port for a short period of time, and you can choose any port that's an output. Great. So you're not tied to the actual constraints of the architecture of the microcontroller. There's one called PWMOut, and that's if you want to send a number of pulses out, this could be the answer for you. If you just want to send out 4 pulses, you go PulseOut, PWMout, number of pulses, and we'll see that, and you can do that to any port. And then you've got this one called CCP, compare. The compare PMWA, we have a fixed frequency, and it's very low impact in terms of the amount of code required. So you can just set the frequency, set the duty cycle, use this timer 2, and literally you set the PPS, job done, works. And you can play with that. It's a great tool to play with in terms of fixed frequencies. And if you're smart enough, you can actually change the frequency as well. It's extremely simple to use, and I'll show you a program that helps you. Then we've got another way, which is using the same module, CCP PMW number 5, variable frequency, variable duty, using different timers, timer 2 typically, where the assembly does all the heavy lifting. It's doing a lot of calculations in the background. You change the frequency, it recalculates everything for you. It's extremely simple to use, and we'll see that. Then you've got the 6th way that we'll be looking at is 16-bit way. Wide range of capabilities. You have to set the PPS as with the previous CCP method. You have to lots of parameters, and I'll show you how you can actually use the registers to change those parameters. And then there's an interrupt way, but I'm not going to show you that today. We're going to come back into that in another day and using a different timer. And again, you don't need PPS for that. But today we're going to look at 6 ways of doing things. Quite exciting. So let's walk the code and view all this in a scope. So I'm now in GC code. You can tell that by looking at the logo. Control B, and I'm going to open up program 241. You can have a look at 240 on your own. It's quite sophisticated. It will show you many different ways, but I use it to test to make sure everything's happy. Control B to shut that down. I've selected 241. I'm going to do one thing once, and then you're going to trust me that everything else is the same. Oh, I will only come back to the header when it changes. Okay, we have a 26Q41 attached. We do. Option explicit, define my variables. And I need to ensure for my first demonstration, which is just turning the LEDs off to generate a frequency, that the PPS is not set. So we can just write to the registers that are called the PPS registers for those LEDs that we want to operate. So set them to 0. This is our hardware map. We've seen that before many times, but here are the 4 LEDs I'm controlling, and they match up with resetting the PPS. Set of constants and setting the ports to outputs is the same header that we've had before. So I won't come back to this unless we actually have a change. Okay. Now, here's the program. Very simple. If you have a do loop, you can actually just turn the LED on and off at high speed. And if I wait 13 microseconds, it will generate me a pulse. Will it? Let's try it. Function key F5 to program it. And I'm going to go out to what I call Zen mode, which is just this mode where I've got everything hooked up. And we will see it program it. Did it program it? Oh, it says, do I have power? Maybe I don't have power. I'll just press function key F5 again. Downloading it. Found it. Great, and it's programmed it. Now, you might not believe me. It's all so fast. No, I'm going to unplug that. The signal on the oscilloscope drops away. Does it? But it did on the on-screen one. The actual web app I'm using to the Rigol has got the signal on it, which is a bit weird. Right, there we go. It's come back up properly. And we can see here on the Gubtronics, we've got a signal here, and it is actually 38. Let me just check that for you. That's 38 kilohertz. How have I generated 38 kilohertz signal? Well, this is a square wave. It's fixed. I can't really change it. And it's a useful way of generating signals. But to be quite frank, it's what's called blocking. If you go and do something else in the code, it doesn't work. So it's a way of generating a signal, a valid signal. And you could do a repeat around this in terms of a repeat loop. And you could send out a number of signals this way. It's a method. It's pulse width modulation. Control B. I'm going to open up 242. I've opened up 242, Control B to shut that window down. Let me just check the header, same header. And here we have a command, which is pulse out on an LED for 13 microseconds. And then wait for 13 microseconds. So what pulse out does, it pulls it out on the LED that you have selected. This could be an address like port B.0, but I'm using a constant. And it's saying put a signal out for 13 microseconds and then wait 13 microseconds. And that's very useful because you can actually do that 4 or 5 times. You can go 1, 2, 3, 4, 5, and you could actually generate quite nice signals. But you can also change the frequency. You can change the shape of the wave by just changing the variable. So if you change the second wait, it will change it. But you're not really in control of what's called the frequency. That's the first on and the first to the next off. You're not controlling it that well. You need to you might need a better way. Now you can see in the signal that's being put on the screen there, as I increase this value here, the shape is now on and off more, and the LED, by the way, accordingly is changing. And you'll see the shape change as I increase that time, but I maintain the on time. I'm changing the off time. Now, why isn't that scope updating properly? I'm just going to go out to the Rigol because I can see it on there it is. It's finally caught up. Okay, finally caught up. PulseOut, a useful way to send out signals. Let me revert that so that the demo's set. Control. So we've seen we can turn the LED off and we can send a pulse on a particular port for a particular time to raise that line high, a PWM signal. Control B. 243. Now this one was written many, many years ago. It's very clever because it's called PWMOut. And you can have 4 channels, 1 to 4, and you can actually tell them, you can say to it what your duty cycle is and how many cycles you want to send. So how many times, how many signals? If you wanted to send out 4 signals or 10 signals, this is the way to do it. Watch. And I'll show you how the setup works in a moment after we've seen it generate the signal. So clearly the Rigol is hanging around here for some reason. I don't know why it's hanging around. Let me just put things back as they were. Where's the Rigol? Oh, it's up here. Oh, there we go. Look, the Rigol has now caught up. I'm going to change the scope now. And it's generating a square wave at a frequency that is determined. And that's determined by your frequency of the chip. But if you wanted to say, right, just send out 4 of these, and then you wanted to go and do something else, and that's something else I'm going to put in here as 1 second in your program, you can just send out 4 signals, 10 signals, or 100 signals, whatever you want. If your motor controller that you're using needs a PWM signal, and it needs 10 square waves, this is a really good way of sending it out using PWMout. It's just programming it. Is it? That took a time, didn't it? And we can see in the little scope down here, we're no longer at 38 kilohertz because that's what my reference architecture was. For some reason, my computer is running really slowly. What normally takes seconds is taking minutes. Now, what we've got here on the oscilloscope, the other one will catch up shortly, is an LED that's flashing occasionally every second. And if I come up to the Rigol and I press single, it's caught 4 signals. Now, where's it caught 4 signals? Let me just show you the oscilloscope. There we go. It's caught the 4 signals. PWMout, 1 channel. You can have 4 in total. I've got a shape of it. I said I want a duty cycle of 127, which is 50% of 255. And I want 4 signals on that channel. This is a method that is extremely useful. So if I just did a single capture on that, and if I changed this number here 4, it would actually change it to, if I change that to 10, it would generate 10. So you can actually generate extremely good signals in GCBASIC without using any PPS or any complexity. Generate signals. I'll save that. Control B, 244, fixed mode. I'll explain fixed mode. I'll come back to my program. There is a difference. The first thing I had to do was set the PPS. I have to use PPS if I'm going to use the CCP mode. And if I look in PPS tool, hopefully I've got it open for us. Here we go. PPS tool. We'll zoom in on that so we can have a look how I did my setup. I selected CCP1. Let me just clear that down actually. If I clear it, it will make it a bit easier. Clear. Clear, there we go. I select CCP1 and here is CCP1. I want it to go on port RB0 and I add it in. And it automatically takes across the 2 parameters that are required in the PPS setup. And because I want all 4 LEDs to look the same, I can literally just select it like this. I can go RB1, RB2, RB3, and each time just add them in and it generates it. Now I can come into the transmit. If I want the transmit, I think that was on RC6. I know it was, by the way. Add that in. I've now got a complete PPS configuration in a few seconds. A little bit easier than using MPLab. Copy that out. It copies it into my clipboard and back into my program. I can literally, let me just take that out of the way. I can literally just cut and paste this, cut that one out, Control V to put my new one back in. An important part, if you're going to use CCP1 or 16-bit PMW, you have to set the PPS. No choice. Once you've set it, the rest of this header is all the same, no different, because it's just the same. Now in the program, to make it work, this is genius by Hugh when he first wrote this. You literally say, I want a frequency, PWM underscore frequency, FREQ of 38 and a duty of 50. And within the compiler, it calculates all the registers and all the bits for you, and you just say PWM on. You can also say off, and then it is running in the background. Don't believe me? Watch this. Function key F5, program it. I'm going into what I nickname as Zen mode. I'm just going to set the oscilloscope, turn that on to run. I'm going to have to sample it in a moment because we were running at a very strange frequency, and we have a frequency coming up. There we go. Let me just scale that for us. There we go. And let me reassure you, that is 38.914 kilohertz at a duty of 50. And if you wanted to change this to, don't know, let's just put it to 24, you just change the constant. So extremely low impact. What I mean by that is it's done all the heavy lifting for you. And once you get your mind around how pulse width modulation works with CCP, you can then manually change the registers, and it just works. If it doesn't work, let us know on the forum, because this needs to work out of the box. So it's just compiling it up. And what I did in here, I've actually added in a little routine that's called show details, which I'll discuss in a moment. Don't know why my computer's running so slowly. Doing a backup. What I'm expecting this signal is to change to a 24 kilohertz signal. It's still at 38, of course, because it actually hasn't programmed it. I've never seen my computer run. And you saw the LED flash. The signal has changed up. It has changed on the main oscilloscope. And unfortunately, you can't quite see this, but that says on the screen here, 24.054 kilohertz. The signal has changed, which is perfect. If you wanted to change the duty, you would literally just come into here and go, I want a 10% duty, and it is running permanently. With CCP, it's running permanently. There is no user code required to make it operate. You set the registers, and the signal is generated through the timer 2, through a set of registers, which I'm going to show you in a moment. I'll put that back to 50. We'll program it. Now I've left in here something called show comments, show details. What I did, I have another program, 240, which you can look at, and that is quite clever because it actually exposes all the registers. And in show details, these are all the registers, and it's essentially a debug program for what's actually going on. And it shows you all the registers have been set by this program. And so it says it's going to set CCP1 con register. It's going to set either something called PR2, which is actually the time period for timer 2, the configuration of the timer, the actual duty cycle itself, and then the clock source. All that is exposed in the serial terminal if you uncomment show details. Uncomment show details. The signal, by the way, has gone back to 38.9 kilohertz, which is not too bad, not too shabby. We'll just program that, and then out in the serial terminal, we will see the results. And here is the terminal. I'm just bringing it in behind our screen here. Just trust me that the magic is going on. See if I can, whilst it's doing all this, I'm going to try and get rid of that. Get rid of that. Get rid of that. Get rid of that. Give us the biggest real estate I can give you, okay? Is that still programming it in the background? I have no idea why it's so slow. I've never seen it this slow, but that's life. Press on. So you can see I'm getting good signals. LEDs are coming on and off. And what we're doing now is generating a set of debugs so we can see all the parameters that have been set in the background through the command CCP1. Why have I got no output? Oh, I disconnected that, did I? Oh, I can see why. The cable's come off here. You just saw me reconnect it. I'm just reconnecting that one. There we go. Get some power on it. Oh, there we go. Great. And it says that the constants that have been set was PWM frequency at 38, duty of 50. It says use the timer 1, timer 2, sorry, and CCP1. 255 is true. And you can see other registers that have been set. So this is the register that controls the actual CCP. Here's the timer period, timer control, the clock source, the timer selection, and it's really strange. With the later microcontrollers, the timer selection is different on those chips. And then this is the high and low parameters for that CCP signal. I'm not going to go into the details of it, because if you just want to use this, you just type in you just come into the program, you type in the frequency, you type in your duty, and use PMW on and PMW off. So if you wanted that to go off after X amount of seconds, you would literally just turn it off. Great. So what we've got is a fixed method that's very low impact in terms of the amount of memory used, the amount of assembly, because it's all calculated. But if we look at Control B, look at 245. 245 is way more sophisticated. It's essentially the same setup at the top. Look, it's got CCP set up in the PPS. So you need to have the same setup. But this time, what we've got is a command like this. Oh, you can't see it. There you go. And if I look at the help on that, click the word, press function key F1. It opens up the help slowly today. And it says on the screen here that the parameters here are quite simple. Which channel, and that channel relates to what you've selected in the PPS channel 1. I think there were 2 channels, the frequency that you want and the duty cycle. And these are variables. So that means that you could change the frequency or the duty cycle on the fly. Let's have a look. So I'm setting it here at 38 kilohertz at 127, and that 127 relates to 50% because you're going to send it a byte value. And this will therefore give you what's called an 8-bit signal. 8 bits being the value of 255, all the bits being set, all 8 bits being set, so you send it a byte value. And so 127 being half of that, we'll set it to 50%. H, hardware, PMW, channel 1, 38 kilohertz, 50%. And down here, if you want to change the duty, I've given you an example of how to do this. You declare a byte. You declare you're going to read in the AD. We've covered reading the AD in the past. Await, and then I'm going to pass it the same command, hardware PWM channel 1 38, and then the value that's coming back from my ADC. So therefore, it will change the brightness. And whilst I was talking, I programmed it by pressing function key F5, and we will see that in a moment, when my computer's made its mind up, to do its funky stuff. Now it's just assembling it using GCBASIC. And using this method, the constraints within the chip frequency, I've currently got it set to 64 megahertz, it will recalculate all the parameters for you. The same parameters we saw on that terminal, but they're all done dynamically. So it uses a lot of assembly to do this. Now, we're going to have to use both oscilloscopes here to watch this. So I'm going to rotate the potentiometer, and down here, you'll see it a lot faster than the Rigol. You can see that as I rotate that, the signal is getting squarer. Now it's full on. It's full. It's now I'm rotating it back, and as I rotate it back, I'm changing the duty cycle. So if I zoom in on the Rigol, oh, there we go. And that's a bit better on the Rigol. As I bring it back, you can see that the duty is getting less. Now it's 0. The LEDs are off. Turn it on. It goes full on. Well, that's pretty fantastic and pretty easy to do. Again, you can use the registers to change the parameters of this, but this is a very simple way of using a pulse width modulation, the CCP module. Nothing else to show you apart from a little bit of optimization you can do. So because there are up to 5 CCP channels in a microcontroller, if you use these constants as documented in this demonstration, you can actually minimize the code size that's generated. So I've said here, I just want to use CCP1. If you wanted to use CCP2, 3, or 4, you set them to true. And if you wanted to limit the number of timers, code that's available, you set the timer source, these constants here, to either true or false. And what this does, this rationalizes the assembly that's generated. And it's not such a critical thing nowadays because chips are so big in terms of their available memory, but it's still a very useful piece of optimization. And inside of the editors, there are shortcuts to actually add all that code. But looking at this in its essence, it's PWM, meaning hardware, the channel, the frequency, and the duty. It's extremely simple to use. Control B. Let's look at the last demonstration. 245. No, is it 246? Oh, let me have a look. 246. Control B. Now, we're now changing. We've used CCP, PMW. We're now going to be using the 16-bit module. And these are different signal generators within the microcontroller. Therefore, I have to change my PPS. I need to tell it that the PWM modules, the 16-bit modules, where they're attached to. And I said I want those all to be attached to my 4 LEDs. It's the same 4 LEDs effectively. If I only wanted one, I would just have one of these, okay? And I've still got my terminal set up. Now, that means you need to do this. And each channel, each pulse width modulation 16-bit channel has 2 signals within it. I'm just using the first one, okay? I'm using the first one, which is PWM11. There's also one called PWM1112, and then the second one is called 21 and 22. If there are more, it would obviously be 30, 31, 32, etc. Now, I have written extensively on this matter to Microchip. This is a form of madness, the way they explain it, but just think it has been a single channel with a single clock source, and you can actually change the duty across those two channels. I'm just going to keep it really simple, okay, and do one. Let's just look at it working, and then I'll explain it. So to make it work, I am going to do some write directly to the registers. Zoom in. So here's my program, and I'll do the setup in a moment. I'm going to set this to 38 kilohertz at a 50% duty cycle. Do loop. It's just going to do it forever. And I'm going to say my duty, it's a variable, and that's a word variable, is aliased to these channels, and these are registers. It's actually the register for controlling the duty cycle. It's called PWM1 S1, and that relates to the channel, or it's like a split. They call it like a split, but think of it as a split. So there's S1 and S2, and they relate to the two channels. And there's a high and low. So I've created a word variable that points into the two registers. That's clever. Then I do a 10-bit read, and I'm sorry about this bit. I wish I could do a 16-bit read, but I can't, okay? Because the chip doesn't do a 16-bit read. I'm going to read the ADC, and then I'm going to use that value and scale it up to a 16-bit value. Look here. So I'm saying here, look, the ADC value that I got from here, I'm going to scale it from a 10-bit number to the maximum for that 16-bit channel. I'll explain that. And the moment you set the variable my duty, it writes it directly to these two registers. It's an alias. So my duty will just get pushed directly into those two registers. Nothing will change until you reload. You have to reload the duty register on the next period event, which is when it gets to the end of the next cycle, it then resets it. If you do not do this reset LD underscore PWM1 con, set it to 1, it doesn't work. It just sits there. Function key F5 to program it, because I've just programmed it, okay? So, alias controls it, and the value of it, the duty cycle, will be set by the potentiometer. But this is a 16-bit signal, so you have got so many different, you've gone from an 8-bit PWM signal to a 16-bit, much more granularity, fantastic level of granularity. It's just programming it at the moment, and it's completed. Now, I'm using the potentiometer here, and as I turn this, the level of granularity, you can, as weird as this sounds, you can actually feel that this is, you have to do a lot of motion to you can feel the sensitivity in the potentiometer on the scope signal. And if I wind that to full on, guess what? It comes full on. Well, that's a highly granular signal, which you might need to control a device. How does it work? It works because we work directly with the control registers as documented in the data sheet. So in here, it's fully documented for you. It says in here, okay, so I just need to turn off the external resets. I set up what's my clock source. My clock source in this case is the chip frequency, whatever it's set to, and it's 64 kilohertz in this particular case. I turn off the LDS for a little while because as I'm changing the parameters, you don't want the PWM to jink. Now this here is your duties. That is the frequency. As strange as this sounds, this register, these two registers control your frequency. And that's calculated as documented in the data sheet. No scaler, no pre-scaler, and here we have the pre-scalers and post-scalers, because you can actually get very granular, very, very fast and very low frequencies by using the pre-scalers and post-scalers. So it's extremely controllable, where with the CCP, it is not. No matches needed. And then I also want to take you into these 4 registers here. And these 4 registers here control the 2 channels that we've got attached to this particular module. So this one here is setting it to 50%. How do I know it's 50%? Because I calculated it. PWM, that's the channel. S1, which is segment 1, P1. And if you look below, it's P2. And this is where the documentation and the whole naming cycle within Microchip world just falls over in a heap. Because sometimes they've got S21 and sometimes they've got S1P2 or S1P1. Look, you go figure it out. These are the registers you need to use. This one sets it to 50%, and this one sets it to 100%. How do I know? I calculated it in the data sheet. Okay. Clear a load of registers in terms of all the interrupts, and then at the bottom, I then enable it. So what I've done, if you can think about it, in PPS, I've enabled the modules. Yep, I've said attach yourselves to the LED ports. I've said, right, my clock source is actual fact the frequency of the main oscillator. No prescaler, so whatever numbers I'm going to give you now, don't be mucking around with them, just live with it. Then I've said I want to use a specific frequency, and I've said that here. Here's my frequency in these two registers, which is the PR. It's actual, the way to think of that is the old PR2 registers. This is a 16-bit register. Then I set the two channels. I set 1 to 100, 1 to 50%. And why did I set 1 to 100? Because I use this value of 694 hexadecimal down here in my program. That told me it was 100% because I calculated it. And then I enable it. And that's it. So you can actually use GCBASIC to write direct to registers. There is no trickery going on here. It is writing direct to the registers, and you're controlling the registers without any complex or trickery by the compiler. You can write direct by using byte variables, aliases, longs, words, use whatever you like. I don't care. It works. Because we can see it working over here. We're right into those registers. I'm changing that value. Fantastic. Works a treat. You can now know why I've got two oscilloscopes. The Rigol web client doesn't work that well. Okay, what else I wanted to show you? That's it. It's a huge subject, okay? A huge subject. I apologize for the length of the video. Next video will be a lot shorter. It's using an external interrupt to control the LED. Basically, what we're going to do is push the switch and we're going to see something happen. It's a very simple one. That was part 14. Enjoy.